of boot camp for this program. Just want to make a few quick announcements about the schedule. So we'll have 2 talks this morning on graph linear algebra. We'll then have a lunch break, and we'll have 2 talks in the afternoon. One on graph data structures, and then another on fine-grained complexity. That'll be, I think, a little synergistic with the one on graph data structures. That'll conclude the schedule for the day, but you should all look at the schedule. That'll conclude boot camp for the day, but there'll be some refreshments after the last talk, followed by a theoretical speaking seminar. So that's it for today. Oh, before I forget, if you have a question during the talk and it's a slightly longer question that might be good to have the mic, if you pause for a second, I will run over with the mic. So just a friendly reminder of that. Anyway, without further ado, thank you very much, Sushant. I look forward to your talk.
Thank you, Aaron, and thank you all for coming for this first morning talk. Let me quickly tell you what we're going to cover today. I'd initially planned that I would continue on the theme of yesterday. We'll talk about eigenvalues and eigenvectors. How do they relate to graph connectivity? Cheeger's inequality, if you've heard of it. I decided to drop that entirely and instead present something somewhat more modern. There are lots of amazing treatments of Cheeger online already. So I'm not sure I would have done great justice to it, but it would also be a disservice if nobody at this bootcamp spoke about graph Laplacian solvers, because in some sense, many of us trace at least the origins of many of these ideas back to a really fantastic work by Spielman and Teng back in 2004 about solving Laplacian linear systems, and I want to build towards presenting an algorithm, a fast algorithm for solving Laplacian linear systems today. I think I should be able to give you an entire proof, but if not, I will definitely present to you an entire algorithm and ideas for how to prove the Laplacian algorithm. Right. So before that, in the first part, we'll begin with graphs falsification, linear algebraic graphs falsification, and in the second half, we'll work towards solving Laplacian linear systems. Right. And as always, any questions, please feel free to stop me. These will be faster than yesterday, second and the third a little faster, but I still believe it's at a level where everyone should be following. So please stop me for questions, right? Please don't hesitate. Thank you. Awesome. So let's dive in. So the first part, we're going to talk about spectral graph falsification. For those of you new to the area, maybe these words make no sense, but hopefully by the end of the first hour, they will. Super. So, sorry, is this not working? Yeah, the clicker is not working, but maybe let's get started. So here's the result we will see today. It's a result by Spielman and Srivastava 2008 that shows a linear algebraic approach to sparsifying graphs while preserving cut structure. This is an informal statement. I will formalize this. Right, so it was the result in 2008, and it's in some sense a very simple result. It was one of the, you'll see as one of the results that really shows you the power of looking at graphs linear algebraic, right? And how some things fall out very, very naturally when you look at these graphs linear algebraically. So let me do a quick recap of what we defined yesterday. So we defined positive semi-definite matrices. So we say a matrix, symmetric matrix A. So a square symmetric matrix A is PST, positive semi-definite, if its quadratic form is always non-negative. Right? And in particular, this implies that all your eigenvalues are non-negative. Right? We defined this yesterday, and because of the quadratic form of the Laplacians are PST. Right? The quadratic form of Laplacians was sum over edges, weight of the edge times xu minus xv squared, always non-negative. So building on PST matrices, let me define a notion of approximation for PST matrices. It turns out to be very nice for dealing with them. I'll define A epsilon approximates B. Think of both as square symmetric PST matrices. I'll say that A epsilon approximates B if, let's parse this, the quadratic form of A is always sandwiched between the like a small multiplicative factor times the quadratic form of B. So it's upper bounded by e to the epsilon, which is roughly 1 plus epsilon, times x transpose bx, and lower bounded by e to the minus epsilon times x transpose bx. Right? This should be true for every x. So the quadratic forms are sandwiched. The other way to think about it is that PSD matrices actually identify ellipsoids. If I look at the set, I wanted to do a 3D image of this, but it was more trickier to generate. So I'm going to draw it here. So if I look at the set x transpose ax is equal to 1, right? It identifies a surface in n dimension, right? Which is an ellipsoid with the eigenbasis of A giving you the principal axis of the ellipsoid, and the eigenvalues determining the scale along the principal axis, right? So in 2 dimensions, you can think of, I mean, it should be a symmetric one. My drawing skills are not that great. So something like this, right? And when I say A and B epsilon approximate each other, you should think of them as follows, that there are these two ellipsoids. They don't have to be aligned, right? But if I look at any direction, this is your x, then the point at which they intersect along this line, they are within 1 plus minus epsilon of each other in all directions. Yes? Does this definition make sense of approximating PST matrices? Like approximating convex bodies. The other way to think of it is, if I scale this up by e to the epsilon, it will subsume the other ellipsoid, and if I scale it down by e to the minus epsilon, it will be completely inside the other ellipsoid. Okay, good. And in our PSD notation, curly less than equal to notation, I can write this succinctly as A is PSD less than e to the epsilon b, and A is PSD greater than e to the minus epsilon b. This is just completely equivalent, but slightly more compact notation. Good. So let's move with that. So it turns out to be a very nice relation. Let me show you some very simple properties that you can verify quickly. It's reflexive, of course, right? Like, in fact, it's true with 0, but any epsilon non-negative, that's also true. It's symmetric, the way I defined it, right? Sometimes you'll see 1 plus epsilon, 1 minus epsilon. I chose to define it as e to the epsilon, so it's a symmetric relation. You have additivity without loss in the epsilon. So if I have A1 approximates B1, A2 approximates B2, A1 plus A2 approximates B1 plus B2 with the same epsilon. And here's the fourth one, which is also interesting. It's transitive up to the addition of error. If A approximates B, B approximates, this should read C, sorry. If A approximates B, B approximates C, then A approximates C with the error being the sum of the two. Question?
I don't think you changed it the way you wanted.
Okay.
Yeah.
But yeah, you're right. Sorry. Sorry. A approximates B, B approximates C. You get A approximates C. Sorry about the typo. So what are spectral graph sparsifiers? Let me define it and then we will interpret it. Right? We say two graphs, G and H, that are graphs on the same vertex. You should really think of them as same vertex set. I will not say same size. Really think of them as the same vertex set. So there's a mapping. We say that G is a spectral or H is a spectral specifier of it. G if their Laplacians approximate each other, right? With epsilon. I should point out I'm using epsilon because I will usually think of these as small, but it's reasonable to think of large epsilon. Right? You can think of approximations that scale like log n, even n to the delta. Right? All of them, the relation still makes sense. It's non-trivial, right? But we say graphs approximate each other if they're quadratic forms of the Laplacians, right? So the quadratic energy is approximated for all vectors. Is the definition clear to all of us? Questions? Right. So if you think of Laplacians as your ellipsoids, they are sandwiched between small multiplicative copies of each other.
What are you defining? You're saying that in that case.
Good. In this case, X. I say that G, like these are spectral sparsifiers. These are spectral graph sparsifiers. I mean, it's not sparse. If H was sparse, it would be a sparsifier. It's a notion of approximation. Yeah,
the graphs are similar.
The graphs are similar. That's the notion of. And if I'm able to show H that is much sparser than the graph I started with, that would be a spectral sparsifier of the. Here's a implication. Here's a simple implication of what this definition gives you. Let me pick my vector x to be the indicator vector of a set S. Right. So this vector is 1 if you are inside the set and 0 outside. We plug this in, we get. But so look at the quadratic form. What happens to the quadratic form? For a quadratic form, we had a sum for every edge. Every edge looks at the difference of the two entries. So if I have an edge that's inside S, both the entries are 1, the contribution is 0. If I have an edge that's completely outside edge, the contribution is 0 because both are 0. Only the edges crossing the set. One endpoint is in the set, one is outside. They'll give you exactly contribution 1. So you will get, this is what I would have defined if I was doing Cheeger's, but now let me define it here. You will get the weight in the graph H of all edges. So plugging in X indicator of set here, you'll get weight in the graph H of all edges that go from S to the complement of S. Right. So it's just a sum over weights of the edges that are crossing the cut. And this is saying that for every cut, not just one, for every cut, the cut values approximate each other. Any question?
G and H.
Okay, thank you. It's showing that that I made this switch very last minute. Sorry, this should be G. Right, so this should be G. And this should be H. Let me fix this. Sorry. So this is H. Right, in line with the above. Thank you. The weight in G, the cut value in G is approximated up to small multiplicative factors in the same. So every cut is approximate. Right? Let me show you an example here. So here's a graph. I have two size 6 cliques connected by a single edge. Right. And I'm for example's sake, let's focus on 2 cuts. Here's one separating the cliques. There's just one edge. And here's one that's cutting 2 vertices from the rest of it. And here I'm building a sparsifier for them. It should preserve the weights of all the cuts, right? So if I look at the cut that separates all of them, It's still one edge, so I don't have to scale it. I can just take the same weight as the original one. Let's say it's 1. But here, if I'm going to drop some edges inside the clique, I have to scale up the rest of the edges, right? So that the sum total of the weight remains the same, right? I started with 2 times 4, 8 edges here, and here I only have 6 of them. So I have to scale them up by roughly 4/3 in order to get the same weight. This was a notion of cut sparsifiers defined actually much before Spielmann-Shrivastava. This was defined by Bengsuru and Kager, 92, if I remember the paper correctly. If somebody can confirm. Right, so they defined cut sparsifiers, objects that preserve all cuts. We are defining something stronger, two graphs where the Laplacian is preserved. The cut preservation is an implication. Right? And it turns out these two spectral sparsification is actually strictly stronger. There are graphs where it's known that you are a cut sparsifier, but not a spectral sparsifier. Okay, so let me formalize the result we'll see today. For every graph, we'll present an algorithm, which is reasonably efficient, but we won't worry about that. We can find a reweighted subgraph. This is a stricter notion than what I introduced. I just said graphs approximate each other as long as the Laplacians are the same. But now I'm saying I will only use the edges in the original graph, but I'm allowed to reweigh them. But the edges with non-zero weight will be much fewer now, right? Like you could start with quadratic number of edges and I'll end up with a graph with only n over epsilon squared log n edges. So if epsilon is constant, n log n edges, such that h is a sparsifier of G. A priori, even the statement is surprising, right? Like when Bengsuru was out, I mean, I wasn't around studying theory, but I assume it was a big surprise, right? That you could preserve all cuts with a much sparser graph. In a similar vein, this was a very surprising, like they'd proven it earlier using harder tools, but the existence of such sparsifiers is a surprise. Right? And today I'll show you both an algorithm and essentially a proof. How do you build these? Question?
How much of this depends on the fact that this is a Laplacian, and would this apply to a quadratic form?
Good. So great question. Let me repeat the question. The question is how much of this applies to the fact that the matrix you're starting with is a Laplacian? Would it apply to general quadratic form? It does apply to general quadratic forms. So if you have a sum of several quadratic forms, very many, you can show, as long as the matrix is PST, you can show that there is a distribution to sample from, so that if you sample n log n of those terms, you will get epsilon approximation. Right? So basically nothing here applies. You just need a PST matrix and like a rank 1 decomposition to sample from.
What's the best overhead?
Running time overhead? Or
epsilon to the -2 log n.
So
is there a lower bound?
good. So epsilon to the -2 is tight.
Yeah.
It comes from Cheeger, actually, right? Like even for the clique, to get a cut sparsifier, I need, and the log n is not tight, even for Laplacians, right? So just the way for a clique, you can have constant degree expanders. You can have for every graph sparsifiers with n over epsilon squared. It's a much trickier proof, but you can achieve it.
For general PST matrices, will you get the same multiplicative approximation?
Yes.
Question?
Yes. Oh, sorry. The question was for general matrices, not Laplacians, will you get the same dependence and approximation? Yes. You'll get e to the epsilon multiplicative approximation with the same 1 over n log n over epsilon squared rank 1 terms, or whatever like decomposition factors you pick.
Just to complete the picture. picture. Do you want to comment to complete the picture of Moses' question? Do you want to comment on the sparsifiability of a single quadratic form?
Can I?
It's just not doable. It's not like if you just have a PSD matrix, you can't sparsify the entries.
Oh,
Yeah, but you can do
let me. Yeah. Let me reset the question. So thanks, Aaron. So I think
We're pointing
this
out the two different.
this is the question. So Aaron is commenting that there are slightly different interpretations of what it means to sparsify, and let me say that explicitly. Thank you. So when I said you can sparsify it, what you can do is you can write a PSD matrix approximately as a sum of rank 1 factors n polylog. If m was a sum of many factors, let's say m was sum over I to rank would be trivial because then n log n is much larger, right? So very many rank 1 terms, vi transpose. Then I can write an m tilde that is an approximation which goes from I1 to n log n and introduces a weight wi vi transpose, where I pick a subset of them. In this sense, you can achieve a sparsification. But if you're looking for sparsification entry wise, right? If I just write down a matrix with n squared entries, can I have a sparse matrix where many entries are 0? That's not true, right? While if you want to achieve a multiplicative parity, and the example is very simple. If you look at the all ones rank 1 matrix, it's you will not sparsify it.
Do you need rank 1 here?
No, you don't.
Yeah.
If you don't mind, can we drop the generalization questions for a little later so that I can focus on the graphs case? If we have questions about graph, I'm happy to take them now. I'm happy to take the general questions in the break too, but I would like to make sure we finish this. Is the theorem statement clear to all of us? What are we hoping to build to? Awesome. Good. So here's going to be our approach. The approach really seems deceptively simple. So I'm going to define a random graph H so that the following holds, that in expectation, my Laplacian of the random graph is exactly equal to the Laplacian of the original graph. Right? And viewed as a matrix. So if you view the entries of the matrix, it will end up being the same. The expectation of the random graph. And 2, we will use matrix concentration. Don't worry if you haven't heard the term before. We will use matrix concentration to show that you can achieve that a randomly drawn sample from this distribution will approximate the Laplacian. Right? This is our high-level approach. And of course, I will spell out all the details here. But the plan is very, very simple. I will define a random graph with the right expectation and show that it concentrates. Good. So let's work with the easy part. The easy part is, how do I define a distribution which achieves the right expectation? Here's what I'm going to do. I start with my original Laplacian. It's a sum. Remember, it's a sum over edges. Weight of the edges in the graph, like this, E is the set of edges of G. Weight of the edge times the Laplacian of the edge. And I'm going to sample a reweighted subgraph. Right? That means I'm going to have the same sum over edges, but now with new weights, WE prime, where many of them will be 0 times the Laplacian of the same edge. Okay? And my sampling process is going to be easy. I'm going to toss an independent coin for every single edge. Okay? Not probability half, but a specially chosen probability PE, specific to the edge. So for every edge, I'll specify, okay, this one I'll toss a coin with probability 1, the other one I'll toss a coin with probability 0.01, right? And I will, so if the coin lands head, I would include the edge, but with a new weight W prime. If the coin lands tails, I will just discard the edge. So the weight is 0. So what is my expectation for this really simple process? The expectation of the Laplacian, well, it's an independent toss for every edge. So I get a sum over edges. The probability that you see that you actually pick the edge times the new weight. PWE prime times the Laplacian of the edge. Right? How many of you have never seen matrix random variables before? Okay, great. So one good way to just think of these is that when I say that the expectations are equal, every single entry, right? So expectation is linear, so I can just look at them entry wise. And entry wise, you get exactly the sum on the right. So I want to match both of all the n squared entries on the left and the right. But really, because all of these, like the relations are linear, expectation is linear, this one is actually very easy to match. Right? Do we all see how do we match the expectations? That's right. Thank you. So we're going to set the new weight to be the old weight over the probability of sampling. So whenever you sample it, in expectation, the multiplying with the probability cancels out the 1 over p, you get back the original weight. So this is called importance sampling. You might see this term at other places. Toss independent coins with different probabilities, and whenever you keep the object, you scale it up by 1 over PE, and this preserves the expectation. Okay? So very easy. This is my random graph process. Right? It's a distribution over graphs H that achieves the right expectation. Questions?
Okay. I guess the random sampling, Benzer and Carter were doing the same thing, right?
That's right. So Benzer and
It doesn't
Carter.
differ in that sense.
That's right. So the comment was about random sampling for Benzer and Carter. Benzer and Carter were also doing importance sampling with the right expectation. Exactly. Right. What the difference here will turn out that in some sense, the achieving the probability distribution is much cleaner here than what Benzer and Carter did. Right. And of course, it ends up being strictly stronger.
Yeah.
The properties we obtain.
Marion, I think, had a very nice proof considering all the different PIs that PE suggested and showing they all give the same results. It was very nice thing, but whatever.
Like the Benzer and Carter? No,
No, that all the different PEs that have been used both by Spielman and David Carter.
Right.
More uniform.
Right. Yeah. There was a bunch. There are a bunch of probability distributions. That I don't see Demala here. Demala is also like bunch of probability distributions that will achieve this. This one will give you a certain specific one, and in fact, any probabilities that are larger than this will work. That we follow. But we also had a question.
Well, how are we going to choose the probabilities?
Excellent. That's the key that we'll move to next.
So you mentioned that there are examples of graphs and sparsifiers for those graphs, which are cut sparsifiers but not spectral.
Yes.
I'm curious, if you look at the probabilities that the PEs that Benzer and Carter suggest, are there also examples where those PEs don't, like using the edge strength or whatever it is they use, doesn't work for spectral?
Interesting question. So let me repeat the question. The question was that we know examples where spectral there are graphs that are cut sparsifiers but not spectral sparsifiers. Is it also true that you see the difference in the two sampling distributions that pop out of these examples? I think you should see it, but I'm not entirely sure. The example actually is very simple. You sort of have a strengthened cycle, right? You have a strong cycle like with heavy edges, and then you have one edge going diagonally across. And for this one, if the edges are, if the if the cycle edges are strong enough, then the edge going diagonally across doesn't make a difference for cut spacification, right? But for spectral spacification, you have to preserve this edge. Right? So I think it will show up in because the importance probabilities of Bexel-Kaga are basically defined by looking at the sizes of the cuts, and this edge is not important for the sizes of the cuts. Oh, sorry, Demale is right there. So Demale had a series of works with very nice ways of. There are other probability distributions, simpler ones than what Bexel-Kaga presented, that achieves cut spacification. Did you also achieve spectral spacification? No, right? Like so for spectral spacification, like this is the lower bound that falls out of Spielmann and Schwarz. More questions? Okay, excellent, good. So then let's see. The probabilities will pop out of building the proof. So let me build up to the proof. Right, we said the main key step of the second process is showing matrix concentration. What is matrix concentration? I will take a very easy view. It's not a comprehensive view. It's not a robust view. Let me start with scalar Chernow bounds. Hopefully all of you have seen them, but let me remind you of Chernow bounds for real random variables, right? Scalar one-dimensional random variables. Here's a particular version. So consider random variables xi that are non-negative and always bounded above by b. Okay. Right? They never take values larger than b, and they always take positive values, non-negative values. And let me assume, by some simple scaling, that the expectation of their sum, or equivalently the sum of their expectations, is 1. So random variables that are bounded, and I know that their expectation is 1, then with high probability, for a second just treat this term as with high probability, 1 minus vanishingly small, the sum is epsilon close to 1. And of course the key is, what is this probability as a function of my variables? It's 1 minus, you can ignore the 2, e to the minus epsilon squared, right? If you want an epsilon approximation, you get an epsilon squared divided by the range of the variables. Right? This is a standard, like it's just, I've just massaged some parameters to write a standard scalar. You don't see it written this way. You'll see typically two, like an upper tail bound, a lower tail bound, with slightly different scalars in both ways. I've just massaged it to say that you get the sum lies between e to the epsilon and e to the minus epsilon, which is just roughly 1 plus epsilon, 1 minus epsilon, with high probability. And the interesting thing is, how is this probability scaling? 1 minus e to the minus epsilon squared by the range of the variables. This is scalar concentration. How many of you have never seen scalar concentration? Okay, great. So this is familiar, but just I'm rephrasing something you've seen before. Now let me present to you matrix concentration. So there is a version of Chernow bounds for matrix random variables that looks basically the same. So this version was proved by Trop first. Like there were previous versions that would have also worked for the proof, but Trop has a very clean version. If you would like to see, the proof is also really very clean. It uses a powerful matrix inequality, but the proof really uses matrix exponential generating functions, which is also how you prove scalar concentration bounds. So here's matrix concentration. This is in some sense the crux of the algorithm in the proof. So please stop me and ask questions if anything is unclear. So I will assume symmetric random variables xi. So these are now n by n random matrices that, similar to before, are now PST, right? They are PST greater than 0, and all their eigenvalues are bounded by B above. Right? So they are spectrally bounded by B times the identity matrix. This is the spectral ordering, right? So, or the other way to think of is quadratic. Their quadratic form is always between 0 and B times the norm of the vector squared. X transpose Y transpose XIX is at most B times the norm of Y squared. The assumption clear on the random variables? And I will do a similar scaling as before. I will assume that the sum of their expectations is exactly equal to the identity matrix. Right. So PSD random variables that are PSD random matrix variables that are always bounded, and in expectation their sum is identity. Right? These are my assumptions. Then you get a statement that generalizes the scalar one. It says that the sum of the random variables is an epsilon approximation of the identity matrix in a PSD sense with high probability, where the only thing you lose is that in terms of the exponentially decaying term, you get a factor of the dimension, n. It's literally the same scaling, epsilon e to the minus epsilon squared by b, but you get a factor of the dimension in front of this factor. That's it. It's like thinking of n independent random variables and getting concentration for all of them, right? And if you did a union bound, you would lose exactly this n. And this says that's enough to get spectral approximation. It's a very surprising result, because if you were to try to prove this from scratch, you would think of, oh, let me take an epsilon net over n dimensions. I will get 2 to the n vectors, and then and then you should lose an exponential term here, right? If you are going to union bound over every single vector, you lose an exponential term there.
Isn't it enough to do no eigenvectors?
No, because the eigenvectors of the random variables need not align. Great question. Let me repeat the question. The question was, is it enough to work with the eigenvectors? And it turns out, no, it would be enough if all of these xi's had the same eigenbasis. But that's not true. I'm not assuming that the xi's commute. I'm not assuming they have the same eigenbasis. But still, in effect, this concentration bound says that the effect is the same if they were commuting.
So it has to do with it, because the proof of carcass thing, right, exploits very much that there's only a polynomial.
That's right.
Does that somehow come in here also when you do the mates?
Good question. So the question asks, in Bengzur and Karga's original proof, they, like, even though there are exponentially many cuts, they work with saying that the number of cuts sort of increases polynomially with the size. So is there something similar here? Yes, I will give you a vague answer, but I think Jilani is the right. So you can think of these as like this sort of falls out of what's known as chaining. You look at a sequence of epsilon nets where a very coarse one, and then a smaller one that's closer, and then a smaller one that's closer. And you basically have to bound the growth of the sizes of these epsilon nets, which, if you squint hard enough, is a generalization of the polynomial growth of cuts. But it's really a stretch to say that these are the same arguments. It's much, much harder here. Is that fair, Jilani?
Yeah, it's true that you can prove it through chaining. I guess.
But would you say chaining is somewhat related to the polynomial growth of? I guess I'm just seeing that the growth of these different scales, how do these grow, pops up both places. That's the only similarity. How do the number of cuts grow, and how do the number of vectors grow with the, like, that growth shows up in both the proofs, but you have to squint really hard.
I should also point out that the kinds of bounds you can get with chaining are strictly worse than what you could hope to get by a more refined analysis. There are better versions of matrix turnoff that exist, and don't know a chaining proof that recovers them.
Good, thank you. I will keep that comment off the record. So the context is very. Yeah, go ahead.
Is there any dependence on the number of xi matrices in this bound?
Excellent. No, there is no dependence on the number of xi matrices. More questions about matrix concentration before we apply it to a random process? Okay, excellent. So let me just rephrase this now. If I wanted to achieve high probability 1 minus 1 over n to the c, I mean let's say n to the 10, then the bound I need on my random variables looks like epsilon squared over log n and a factor c, like depending on how much high probability you need. Right? For standard concentration, you would not have the log n factor. You only wanted everything to be smaller than epsilon over c, and now you get epsilon over c times log n. So if I have every random variable, every random matrix is smaller than epsilon squared by log n, then I get that it approximates the identity matrix with high probability. Okay, how do we apply this to our process? So let's recall, what are our matrix random variables? We are going to have a random matrix variable for every edge. Right? So my random variable is as follows. I mean, maybe you can think of this as xi or xe. For every edge, I get a random variable which takes the following values. The probability 1 minus PE is just the zero matrix. But with probability PE, when I decide to keep the edge, what do I contribute to my sum? I contribute the new weight, which is the old weight by the probability of sampling, times the Laplacian of the edge. Right? So the Laplacian of the graph I output is exactly the sum of these random variables, xi. Agreed? Questions? This is our definition of random variables, right? But this is funny because we wanted that the sum of their expectations should add up to the identity matrix. But here, the sum of the expectations adds up to the original Laplacian. You can fix this by a pretty standard linear algebraic transformation, but if you haven't seen it, it might seem magical. You can fix this by multiplying each matrix xi on both sides with a matrix that's effectively the inverse square root of the Laplacian. Okay, let me take a second to say how should you think of this if you've never seen this. So here, if I have a matrix M, inverse square root of the Laplacian is a matrix that if I square it, multiply it by itself as a matrix, right? I get the inverse. Right? But but how do you compute, like, this is an existential question, right? But here's another way to think of it. If I was to write the matrix in terms of its eigen decomposition, lambda I, vi transpose, and for simplicity, just assume that all the eigenvalues are non-negative. Then the m to the minus half matrix just applies the power minus half to the eigenvalues. 1 over root lambda I, vi transpose. That's it. And you can verify that squaring this gives you 1 over lambda I, which is the inverse of the matrix. Right? So for every PSD matrix M, there is a suitable m to the minus half. A term sometimes can get thrown around. This is what's called whitening. You don't have to remember it. Like, if you see it, this is what is called whitening the data. So if I multiply each of these samples with the inverse square root of the Laplacian of the original graph, then in expectation I get the identity.
So again, it's just a technical matter. It's singular. So
yes,
zero, but
thank you.
Okay, you didn't really want to hear that.
Thank you. So Philip is pointing out whether Laplacian is singular, is the square root defined. I'm going to shove that under the rug. It's fixable.
Yeah.
But it actually needs massaging of the proof also. But you can sort of think of it this way, that there is an orthogonal direction where each of these matrices will have a kernel. So there is basically no randomness in the orthogonal side. So I can just work on the subspace orthogonal to the all one spectrum. Right? Conceptually, that's enough. But to make it formally work, it would have made the proof a lot more uglier. So I'm going to skip. But the right thing to do here would have been basically the square root of the pseudo inverse.
Yeah.
Okay, I have a typo there. This should read sum of expectations. Right, so in expectation, the sum of these random variables is identity. Right, now these are new random variables that sum up to the identity. And it's here's actually another property that I did not specify, right? So let's go to the other side. Suppose you are able to prove that Laplacian g minus half, Laplacian of h, Laplacian of g minus half is epsilon approximates the identity. This is in fact exactly equivalent to proving that the Laplacian of h epsilon approximates Laplacian of g. And the way to do it is translate this statement into quadratic form, and you get L Laplacian of g minus half x. You replace x with Laplacian of g half times y, and then the inverses cancel. You get the quadratic form of h on the left hand side and the quadratic form of g on the right hand side. So it's a simple linear algebra exercise to show that these statements are exactly equivalent. So it would suffice if I showed you concentration for these random variables in terms of the identity. Questions? Is the goal clear? Okay, super. So here's a notation I like for presentations. I'm going to color a random variable x and say this is an isotropic position. I mean, it's been whitened. So red x is the Laplacian minus half times the original x Laplacian minus half. Okay, I'll keep the definition up there so that so we have a random variables.
So it should be red xi.
Yes, sorry. For every x, this is just a definition. What is a red x? Michael, question? Can I? Okay. Yeah, but if you have a question, happy to. So in this notation, we have summation of expectations of these red variables is exactly identity. So in order to apply, so these are PSD matrices with their sum of expectations exactly identity. So in order to apply concentration, there's only one step remaining, is to bound their sizes and bound the spectral norms of these random variables. Right? So we need to achieve that the spectral norm of the red variables is smaller than epsilon squared by log n. I'm going to ignore constants just for simplicity. Okay, what is the norm of these variables? So whenever there are only two cases for every edge, right? If you don't sample it, it's a zero matrix, the norm is zero, driven. So the question is, when you actually sample it and decide to keep it, what is the norm of the sample, right? Not of the expectation, what is the norm of the sample you drew? So the norm of the sample is, so the edge we included was with weight WE by PE. I know I've not specified the probabilities, right? But for every probability, we can do this analysis and it will pop out what do the probabilities need to satisfy to get concentration. But so you get weight over the probability, the Laplacian of the edge But because I'm looking at the isotropic variables, you have a Laplacian minus half, Laplacian minus half on both sides. Right. Norm of this matrix. We want this norm with the weights to be small. Yes. Questions? Okay, so now I'm going to do some linear algebra trickery. Here is just a definition, right? So we defined, when we were defining the Laplacian of an edge, we also observed that it's an outer product of the vector 1u minus 1v, right? A vector that has 1 on u minus 1 on v, 0 everywhere else, and you get the vector times the vector transpose. So just substitute that definition here. Now this is a rank 1 matrix, right? If I view this as a vector, right, vector z, this is z times z transpose, the norm of a rank 1 matrix, right? Like it's a rank 1 matrix, it only has one non-zero eigenvalue in the direction of the rank 1 factor, right? So its norm is basically the same as its sum, its norm, the largest eigenvalue is the same as its sum of eigenvalues, which is the trace, right? Which allows you to apply cyclic property of trace and get this as an outer product. But here's another way to think of it. Rank 1 matrices are very simple. If you have a rank 1 matrix z transpose, its leading eigenvalue is just the norm of z squared, right? And its eigenvector is z. So if I I get the norm of this matrix, and what is the this vector, and what is the norm? It's the vector transpose times itself. So you get 1u minus 1v transpose Laplacian inverse 1u minus 1v transpose. Can I explain this manipulation
Go over
again?
that step again.
Yeah, so it's a rank 1 matrix z transpose. We are looking at the norm of that matrix. The norm of that matrix is exactly the norm of z squared, norm of the vector squared, which is z transpose z. So I write z transpose, the matrix times Laplacian minus half times the vector, and the minus halves multiply to give you the inverse. So you get 1u minus 1v, Laplacian inverse 1u minus 1v. Yes? Okay. I want this. So it turns out this quantity 1u minus 1v transpose Laplacian inverse 1u minus 1v actually is a very nice interpretation in terms of the graph. When you think of the graph as an electrical network, right? We derived this yesterday, that if I have demands d, my voltages are given by the Laplacian inverse times the demands. So this can be interpreted as I want unit current into vertex u and draw it out of v. Multiplying it with the Laplacian inverse gives me the voltages in the network. And then when I take an inner product with 1u minus 1v, I get the voltage difference across uv. So what is the voltage difference across uv that will send 1 unit of current? And this is what is called exactly the effective resistance of uv. It's like replacing the entire network with just a single resistor across u and v. What is the size of that resistor is given by the effective resistance. So what do we want? We want, like, it suffices by our concentration to pick the weight WE by PE times the effective resistance. This is exactly the expression that came out of the bound of the norms, to be like it smaller than epsilon squared by log n, but I'll just pick it to be epsilon squared by log n to pick the large, like, to get the smallest probability of sampling them. And now I just rearrange. It says that my probability of sampling an edge is exactly proportional to the weight of the edge times the effective resistance multiplied by a log n over epsilon squared factor. So every edge, its importance is proportional to the weight times its effective resistance. Right? And just pops out of the need for applying matrix Chernoff ones. Right? And once you pick these probabilities, my matrix Chernoff bound goes through, and you get a proof that the Laplacian of H with Laplacian, original Laplacian minus half approximates the identity, which is the same as saying that the two Laplacians approximate each other. Yes. Excellent. So that is a caveat that I cheated.
What's the question?
The question is it easy to see that the probabilities are between, as I defined them, are between 0, 1? They're actually not. I will give you a fix of this. The same proof is fixable. But for now, just assume for some reason that these were always smaller than 1, and it would be okay. Right? I will fix that. But before that, I'm actually going to show you something else.
Let me do my own thing. So the motivation to get here was to show that the eigenvalues are bounded, essentially.
That's right. Of the samples.
Yeah.
Yeah. The motivation here was that in order to apply matrix Chernoff,
Deterministically bounded.
yes, in order to apply matrix Chernoff, I know I need my samples to be always upper bounded by epsilon squared by log n. And that, like, the probabilities just popped out of it.
But specifically, the eigenvalues have to be essentially.
Yeah, so the matrix has to be spectrally bounded by epsilon squared by log n, which is the same as saying that the largest eigenvalue is bounded by epsilon squared. Okay, so one more thing. The weight times the effective resistance is often called the leverage score of the edge. Right? Effective resistance does not have the weight incorporated into it, but once you multiply it by the weight, then it's called the leverage score. So here's another way to think of it. For 0 weighted edges, you still have an effective resistance, but the leverage score is always 0. Okay, this is a definition often seen and often useful, and we'll use it in the second half of the talk. So there's just one step I need to wrap up. What is the number of edges we sampled? Right now I just showed you, oh, if you pick these probabilities, you will get the concentration. But if that's all I wanted, I would just keep the graph, right? So I need to show that you have sampled only a small number of edges. I'll just calculate the expected number of edges. You can make this a high concentration bound, but let me just calculate the expected number of edges with positive weight. So at least the summation is easy to write. Sum over probabilities of keeping the edge, log n over epsilon squared, sum of leverage scores, weights times effective resistances. Now I need some more linear algebra. This is just the definition of effective resistances, 1u minus 1v transpose, Laplacian inverse 1u minus 1v transpose. But this is a scalar, right? One-dimensional entry. So I've just introduced the trace operator here, right? Trace of a one-dimensional matrix is just that entry. Trace has very nice properties. Trace allows you, trace of AB is the same as trace of BA. You can sort of cycle around the entries without, while preserving the trace exactly. So I'm going to apply two properties of the trace. First, linearity. So by linearity, I can bring the weight in. Do I have another step here? Yes, I think I do. Good. So I'm going to use linearity to bring the summation inside, and I'm going to use the cyclic property of the trace. So by cyclic property, I'm going to first move this vector out here. Right. So this vector here, that gives me 1u minus 1v, 1u minus 1v transpose. Right. And that sort of isolates the Laplacian on one side. I guess the way I've done it is you take this vector and put it at the end. So the Laplacian comes up front, is first, second, and third. So the Laplacian I can pull out by linearity. The second and the third entries are here, and the scalar I've pulled in again with linearity, sum over weights. Sum over edges, weights, 1u minus 1v, 1u minus 1v transpose. This is exactly my original Laplacian. So this is just the trace of Laplacian inverse times the Laplacian, which is identity. So it's bounded by n over epsilon squared log. So in expectation, I've only sampled n over epsilon squared log n edges. Right? Yes. Oh. Excellent. I will. So the question was, can you compute these effective resistances quickly, efficiently? They can be computed in poly time. This is just a matrix inverse. But you can actually compute them really, really fast, almost linear time. But let me drop that question maybe to later, right? Like the key piece is to be able to solve linear systems in the Laplacian fast. That we'll see in the second part of the talk. You combine that with Johnson, Lind, and Strauss, and you're able to estimate them. Really, in m poly log n time, you can estimate all of them rather than just one. And that suffices to get the probabilities quickly, and then you can draw and make the sparse supplier. Okay, and I believe this is the end of my part, the end of the first part. A caveat that I didn't that was raised was that the way I've defined these probabilities, it can be larger than one. But let me tell you, you can do this without loss of generality. Why? If I split one edge into k parallel edges with weights that are scaled down by k, WE by k, then each of these has a leverage score that's smaller by a factor 1 over k. You can basically treat them as different edges. Nowhere in the proof did I assume that there were no parallel edges. So you can have parallel edges with smaller weight and their leverage score goes down, and it does not affect the output of the procedure or the concentration probability. Right? So just divide each edge into log n copies. Each of them gets a leverage score of 1 over log n, and now you can apply the same probabilities. The same proof goes through. But it turns out actually with a slightly more involved proof, you can just do the following, that you just keep all edges. If your probability, this expression is larger than 1, just keep it deterministically and do not do any sampling. But the proof is trickier. Like you have to work with the randomness a little more carefully. Okay, I think that's that first section.
You get an extra factor of log n in the sparsity bound.
In the sparsity bound, no.
Well, you've got k parallel.
So my sparsity bound was completely independent of how many edges I started with. Right? My sparsity bound that I achieved was just n log n, independent of whether I started with n squared or in fact n to the 10, where many of them are parallel. I don't care. You will end up only with n log n edges. Right? That's why this really is it's a complete proof. You'll usually not see this because you can just ignore and not do random sampling on the ones that get Q larger probabilities. But the proof needs more work. Okay, I'm happy to take questions, but I think that the time is really over. So maybe.
So first, thank you.
Thanks.
Thank you very much. Maybe we'll take one question and then go into the break if someone has one. Okay.
Is there a deterministic algorithm with the same number of edges?
Excellent question. The question is there a deterministic algorithm with the same kind of problem? Yes, if you're willing to pay a lot more in running time, right? Because you can basically compute all the, you can execute the proof of matrix concentration quite explicitly, but the runtime blows up to a large polynomial factor. To do it efficiently, I think you need almost linear time to produce any kind of spacifier. And I don't think you can achieve, you need m to the 1 plus epsilon running time, and in fact m to the 1 plus epsilon edges to do it completely deterministically. So you need almost linear number of edges if you wanted your entire algorithm to be, we don't know If you wanted your entire algorithm to be deterministic, we don't know of an almost linear time algorithm that generates a sparsifier with n polylogons.
I found linear time. Yeah. But he's just asking deterministic, no?
Yeah, I'm saying only deterministic is easy because you can just compute all the matrices very explicitly.
Even polynomial time, we know how to do that, right?
Yes, yes, in polynomial time. Yes, sorry, I was thanks, Delaney. So you can do it in like large polynomial time deterministically because you can execute the entire proof of the matrix concentration bound and convert it into what's called pessimistic estimators. Basically, track the trace and pick the best options. So you can do it in large polynomial time to get the same proof. But if you wanted like really efficient algorithms, we do not know something matching this sparsity.
So I even meant there's BSS.
Yeah, there's BSS.
It's even better in deterministic.
Even better, no?
Yeah.
Good, thank you. I mean, but it's the same running time complexity. They also work with traces of matrices. You do the same here.
So on that fantastic open problem, we'll end the session for now. We'll have a break until 11 o'clock, and then we'll come back to the talk. So let's thank Sushant again. And see you all at 11.